Okay, so I'll be discussing question number A and B. Okay, is my screen visible? Uh, So, first of all, let's look at question number A. So, you are given an integer n, and you need to construct a permutation from 1 to n using integers from 1 to n such that the following condition is satisfied. This is the condition. Basically, the mod of the next, the like AI mod AI plus 1. So it's asking us to do that and make sure that this condition is satisfied. If you are mod, uh, you can output any of them. Right? So this question is kind of very simple. Like, um, first of all, what is what is I plus one mod I? It's just one, right? Except for when I is zero, I is one. So if I is one, the value would be zero. For it, it will be zero. Otherwise, it will be one. So if we print it in descending order from n to one, it should satisfy the condition, right? Because let's say n. So this will be n minus one. So n mod n minus one is one. So it's one. Okay, fine. N minus one mod n minus two. That will be again one. So greater than equal to is so equal to is allowed. So it will be one. So by this, you can continue doing this. And at the very end, there will be 2 mod 1. And 2 mod 1 is just 0, since lesser than is also allowed. So it will work fine. Let me show you the code. So yeah, that's the implementation part. If you look at here, let's say, yeah. So let's look at 5, 4, 3, 2, 1. 5 mod 4 is 1. 4 mod 3 is 1, 3 mod 2 is 1, and 2 mod 1 is 0. So by this logic only, it will continue on forever. So is there any doubt? This? Do I need to repeat anything? Okay, let's move to the next question. That will be question number B. So you are given n chairs in a row. You are given a permutation of length n. Now you have to play a game. You have to visit each chair sequentially, starting from first chair at the ith chair, and you can do the following. If the ith chair is marked, the game ends. Otherwise, you can sit on the chair or skip it and move to the next chair. If you choose to sit on the chair, then after standing up, you mark the pth chair and move to the next chair. So basically, what it is asking us to do is that find the maximum number of chairs given that you can mark a chair. For example, you are this is a set of this is a permutation. So you are at the first index. At the very first, you will be starting from first to n, assuming one base indexing. So here the value is 3. So if for example, let's say you decide to sit here, then chair number 1 will get marked. And what does being marked mean? That once you reach there, you will be 3, then you will go to a 2, and then eventually you will reach 1. If you reach 1 uh, and it is marked, or any chair you reach, it is marked. The game ends there and there already. So you have to find that maximum number of chairs you can sit on using this sort of algorithm. So one solution might come to your mind is, which I have personally implemented, is a simulation-based implementation. First of all, let's discuss this 3 to 1. So the most amount of chairs you can sit on is 2. So how can that be achieved? It's explained here. You visit chair 1, then mark it. So number 1 gets marked. Then you visit the second chair, and you mark second chair. Then you visit the. By the way, if you mark the same chair and like you are at second and you have marked the second chair only, the game doesn't end. And then you visit the third chair since it is marked because we marked it here. The game ends. So this is the basic algorithm. I hope that everybody understood the question well. Now coming to the solution. So there are two solutions, two ways to solve this. One is a simulation-based solution, which I personally use. So what the idea essentially is that, say we are 3. So I will always choose, whichever the ith index I am on, I will always choose to sit on that chair. Okay. So say I'm on third chair, so I'll choose to sit on it. When I choose to sit on it, number 1 will be deallocated from me. Then I'll sit on second chair. Again, it will be deallocated, but I've already sit on it, so it doesn't really matter. And then when I'm in chair number 1, I will still sit on it. What I'll essentially do is that I will unmark chair number 1 and get rid of the count that I had because I had sit in chair number 3. Now, why does this work? Because see, uh, if 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 for some reason I don't unmark chair number 3, then obviously the game ends. So it doesn't really matter for me. Uh, that whatever the values are, let's say there are 100 values after it, so it doesn't really matter to me. But if say I unmark this chair, then maybe this was the most optimal. Then I'll keep a track of the maximum answer that I've reached in the entire series of operations that I've done till now. So I'll unmark it and I'll add 1. So essentially, the difference that has been created due to this chair being added and this chair, this permutation being added and this being removed, is nil. So it will always be optimal to go via this, and we'll obviously find the most optimal answer because it never reduces; it only increases. So I hope the explanation was clear about this uh, code which I'm going to be using. Let's take another example here. Um, so at we are at fourth, okay, at the first index, and the value is 4. So the fifth one gets marked. Okay, good. So we are at third. The third one gets marked. The answer is 2 till now. And then we come here, and then it's already marked. So what I'll do is unmark it. So till now the current was basically 2. Now I'll unmark it and make it 1, and then I'll again mark second one. So essentially going back here to mark the third one, the 3 value or the second index, and the current will again be 2. And then I'll go here, it is also marked, so I'll unmark it, and the fifth one, basically this one, becomes marked, and then I'll again go here and again unmark it. So this continues, and we see that for the entire array, the most optimal answer is 2, which we have reached 3 times here. Same, you can same simulation you can try here as well and here as well. So basically, we have to keep a track of the maximum that we have achieved in the entire series of operation that we did. Right. So this is the code for it. So first of all, it took in the input, and then this is the mark that initially none of the chairs have been marked. Since I'm using zero-based indexing, that's why I've used vi -1. So the current number of chairs that have been sat on, and the maximum that were sat on in any series of operation. So if marked is equal to I, if it's marked, then we'll unmark it and we'll mark the chair that this one is corresponding to. And then if it is unmarked, then we will mark it and the value increases the number of chairs you are set. In this case, it won't increase, neither it would decrease, because we are essentially removing one chair but also adding one simultaneously. So is the explanation clear? Okay. So I'll be moving to the second solution for this code. This is the solution. So first of all, let's establish this. If for some reason I decide no that I will mark a forward chair, but what I mean by the forward chair, say we are here, so I'm marking this. Like if I choose to sit on the first chair, I'm marking this guy. It will always be unoptimal. Why? Why am I saying this? Uh, say whatever sequence of operation took place here, it really doesn't matter to us, right? Because we are talking about this two chairs specifically. So let's say I choose to not sit here, then I can always sit here. Nobody's stopping me, right, from sitting here. Maybe there might be some series of operation in the middle which might stop me, but we'll discuss that. So if say I choose to sit here, I cannot sit here, and I also lose access to this. But if I choose not to sit here, I can always sit here, right? So this is that. So if, for example, we ignore this, now you may say, hey, if we choose not to sit here because of some operations, we won't be able to sit here as well. Come to here only. Like one of them will block us. Okay. If I assume that to be true, can't we just what we did here with 4 and 5? We can also do with these two guys as well, right? We can treat them also similarly. So as you look at smaller and smaller subset of things, essentially, uh, for example, 3 2 here, or maybe there might be 100 elements. It will always be optimal to sit on the whichever value is lesser than. So basically, what I'm saying is that we will only sit if p of I is lesser than equal to I. You will find that this is always true. Because if say I choose to sit on a chair which blocks the forward chair, I can always sit on that forward chair later on, right? So say if I choose not to sit here, then you may say we have to choose here. Okay, I'll not choose this one also. I choose this guy. So it blocks this one. So that's not much of an issue for us because we are not going to the left direction, we're going to the right direction. Then I will sit on this chair as well. Now again, the same rule applies. So we'll not sit on this chair, we'll sit on this. So you get the 2 as the most optimal answer. You can try this with all 4 of them and you will see that this is only the most optimal solution for picking chairs. Am I clear? Like everyone understood? Or should I repeat it?
Bhaiya, so basically it is like most of the part of it is like observation based, right?
It is,
Like,
yeah, you can say that it is an observation based because, for example, when I choose to sit here, uh, sorry, let's say here, I am saying that I won't be sitting in a chair that will come in some time later, and maybe some steps later on. So I can sit on that one also. Nobody is stopping me from that. So I choose that.
okay, Bhaiya.
Anyone else? Okay, okay, that will be it from my side. So will be I will discuss question number C.
Hello, can you see my screen and hear me? Okay, so we'll just discuss C1, which is the easy version of this problem. in this problem, we've been given two arrays A and B of length 10. And in this easy version of this problem, B of I is equal to A of I. So basically, we've been given the same array, so we don't really need to worry about that. Now, for each index I of array A, we can perform the following operation at most once. Basically, we can choose some integer m, which is less than equal to B of I. And that means since B of I is equal to A of I, so we can choose some m, which is less than A of I, and we can set A of I to m. So after that, we can perform this operation arbitrary number of times. But the thing is, we can perform this operation in such a way, we can only perform this operation basically when if we take any subarray, suppose we take this subarray or we take this subarray, basically the GCD of the original subarray in the original array should be same after we have made the modifications as well. So for example, if we take 4 and 8, if we take just this subarray, the GCD here is 4, right? So if we modify any of the elements, the GCD of this subarray should always be the same. It should always be 4. Similarly, for all possible subarrays of this array, the GCD should not change, right? This is the constraint of the problem. And finally, we have to determine the maximum number of operations that can be performed while ensuring that this condition remains satisfied. Okay, has everyone understood the question? Okay, so I hope the question is clear. Now, here there is something which, if you know, this makes the question much easier, which is this property of GCD, right? So suppose we need to find out the GCD of three numbers. Let's take GCD of A, B, and C. Excuse me for my handwriting, but we take the GCD of three numbers, right? This is equal to GCD of A comma B. Then we take the GCD of B comma C, B and C, and we take the GCD of this whole thing. GCD of this whole thing. So basically, if we have three numbers, let's take, for example, let's take 3, 9, and 12. So the GCD of this entire subarray is equal to the GCD of this and this, which is 3. And it is equal to the, and we take the GCD of this and this, which is also 3. And we take the GCD of this, so which is also 3. So basically, the GCD of this entire subarray will also be 3. So now we have come to this simplification that instead of looking at the entire subarray, we just look at every adjacent pair. Because suppose we have one element here, we have one element here, and we have other elements here, right? So if we just look at this GCD, that then we don't have to worry about this GCD, because once we look at this GCD and we include this with the GCD, this is the same as taking the GCD of the entire subarray, basically. Does this make sense? So for, again, let me give you a simpler example. Let's look at one of the test cases. So let's look at 8, 10, 10, 12, 12, 14, right? So basically, if we are modifying, let's say we are modifying the element 8 here, okay? We're changing the value. That means all of the subarrays which include 8, which is this subarray, and which is this subarray, and which is this subarray, all of these subarrays, the GCD should not change, right? So the GCD should remain constant. So suppose we just take the GCD of these two elements, and then when we include this third element, we don't need to take the GCD again of all of these elements, right? We could just look at the previous GCD. Similarly, when we're at this element, if we already know the value of this GCD, we just need to do GCD this and GCD this, basically, right? So with this, there is a very simple solution for this. For any element, the GCD of this element and this element, uh, it should be the same. So for example, let's take this for example. So we have 1, 2, 3, 4, 5, 6, 7. So the GCD of 4 and 5 is 1, right? That means we can set this element to 1. Again, for this, let's just consider a small array with 8 and 10. We have 8, we have 10. Suppose this is our array, right? What will be the GCD of this? Or let's take 8 and 16 actually. So the GCD of this is 8 itself, right? So that means if we are considering just this array and we check the GCD with the previous element, so we can set 16 to be equal to 8, right? And suppose we have another element in the future as well, right? 32. So again, we check the GCD of these two elements, right? So the GCD of these two elements is 16 and 32 would be, I think, 16 itself. So the GCD of these two elements is 16. That means we cannot make this element any smaller than 16, because if we make this element smaller than 16, that means these two GCDs, the property will not be satisfied that the GCD should not change, right? So we cannot change this element. Why? Because if this 32 did not exist, we could have made this 16 equal to 8, because the GCD here is 8. But since this 32 exists on the right side, we cannot change this. Now, finally, we have three elements again. Let's take 8, 16, and 8 again. Again, the GCD of these two elements is 8. So we can actually change this to 8. The GCD of these two elements is also 8. Again, so we can change this, right? No problem at all. So basically, for every element I, we need to check its GCD with the previous element I minus 1 and the future element I plus 1, right? And for any two elements, we can set I equal to the GCD if it is lower, right? But this should be true for this also and this also, right? So the GCD of I, A of I and A of I minus 1. And we should also take the GCD of A of I and A of I plus 1, right? Both of them should be satisfied. So what number can we make A of I such that both of these properties are satisfied? Again, let me take a simpler example. Let's take 3. Let's take 6, and let's take 24. So the GCD of these two elements is 3. The GCD of these two elements is 6, right? So if this element did not exist, we could change this value so that it is equal to 3. But this value also exists, right? If this 3 did not exist, we could have kept this 6 as 6, which is the GCD of these two numbers. But now we have to ensure that the GCD of the left side is also satisfied, GCD of the right side is also satisfied. So we just make sure that this current element is equal to the LCM of these two GCDs, basically. So LCM of 3 and 6 is 6. That means if we can set this element to 6, then we can do some operation on it. But since this is already 6, that means we cannot change this value at all. So if you look at the code, is this understood? Does someone have a doubt? You're free to ask. You can also write your doubt in the chat if you have something. But anyway, basically, this is it. You need to satisfy the GCD on the left side. You need to satisfy the GCD on the right side. How do you do that? Both at the same time, you take the LCM of these two values. So finally, when we look at the code, so we just take the input. This is fine. Now for the first element, we don't have to check both the sides because for the first element, there is no left side. So we just check the GCD of the current element and the right side, right? And if A of I is equal to, if the zeroth element is equal to the GCD of the first element and second element, then we cannot modify that, right? Similarly, we do the same thing for the last element, right? And finally, we iterate over all the elements. So for some element A of I, we find out GCD of A of I and A of I minus 1. For again, for A of I, we found out the GCD of A of I and A of I plus 1, right? And finally, if A of I is equal to the LCM, so this formula is just to find the LCM of the two values of L and R. Why? Because there is a formula that A into B equal to GCD of AB into LCM of AB. So A into B is equal to GCD of A into B, A comma B into LCM of A comma B. So we can use a formula. We can use that formula basically. Yeah. So if A of I is equal to the LCM, we cannot modify that. So I have marked this in this array. Finally, there are n total elements and we subtract all the values which we cannot modify. So this accumulate function is it just finds the sum of an array. So since we have marked all the values which we cannot with 1, accumulate will give us the number of ones in the array basically. So yeah, so that's it. That really was our answer. If anyone has any doubt with the LCM GCD, how to prove the thing, you can find out that proof actually. GCD of multiple elements. This is the actual statement you can use. So any GCD of multiple consecutive elements can be broken down into a series of two-number GCD calculations. You can look up the proof later. Yeah, but that's it. If anyone has any questions, I can answer them. Otherwise, we can end the meet. Okay, cool. Thank you so much.